Well, welcome. I am recording. This is so we normally have senior lunch at 11:30 on Thursday or on Fridays at the North Liberty Community Center. But since COVID hit, we had to. It's still nice to get together and see each other's faces and talk to each other. So the socialization part we can do on Zoom. If you know of somebody that needs help with tech to get access to our Zoom presentations, you can contact me. You know how to reach me through our Facebook group page, or I do have a senior squad email that I send, maybe one email a week, usually reminding you the topic of this Friday and maybe like a follow-up to some of our discussions, to send links to things that we talked about. We hope to resume senior programming at the North Liberty Community Center in the spring. So usually we have Tuesday and Thursday afternoon programs, some really cool topics, and then our Friday lunch at 11:30. So we'll see what happens. I mean, it's all up in the air. But I'm going to let Ray take the floor. And like I said earlier, he did a presentation on Iowa landforms earlier this year, which was really cool. And that was in person, though. Boo. Can't see each other every day now, or every week now. But I'll let you go ahead and go. It's your...
Alrighty. Well, I'm gonna give you a little presentation about the two meteor craters that we have in Iowa that we know of. I'm sure there's more, but the two that we know of, and I've been lucky to really work a lot on one of them, and a little bit on the second one. The second one was coming down about the time I retired, so I wasn't working on it through the whole program. But I'll share my screen and see if everybody can see this. How's it looking? Good. Okay, then we'll get started here. I call these things impact structures because when you say the word crater, you think about a hole in the ground, and these guys are all sort of filled in, so they're not really a crater per se, not a hole. They're just used to be a hole, so that's an impact structure. Okie dokie. Here we are in North Liberty, and we have two impact structures in Iowa. The one is pretty big. It's way over here in western Iowa, called the Manson Impact structure. And the other one we've just been working on for about the last 6 or 7 years. It's called the Decorah Impact structure. We just discovered it. We knew there had been something weird going on up there, but didn't know exactly what it was. So anyway, let's start out talking about Manson there, because that's the one that's near and dear to my heart. About 150 miles away to the northwest of us. This is a Skylab picture, an old Skylab. I don't know if any of you remember Skylab, but that was one of the first orbiting laboratories. But they orbited kind of at an angle, and they took the pictures at an angle. So these pictures are tilted, and I just kind of left it that way because this is the first time I actually drew a circle around what I think the limits of the Manson crater are. You can see it's pretty big. It includes parts of 4 counties. This is it here. Now, I mentioned it was pretty big. These little white lines that you see zipping across the thing here, these are section line roads. So these are roads a mile apart. So that gives you an idea how big this crater is, 23 miles in diameter. Here are some of the towns around there, the town of Manson. Can you see my cursor?
No.
No, I'm afraid of that.
Oh.
I don't know how to make the cursor visible in this thing, so I can't point. I'll just have to talk. The town of Manson, near the center of the crater, is what gives the crater its name. Although the feature that I point to when people want to know where the center of the crater is this Kelso Prairie. It's a little 2 or 3 mile square prairie out in the middle of a wild prairie out in the middle of the area there, and it's very close to the center of the crater. Anyway. This turns out to be the 25th largest known impact structure on Earth, and that's pretty good. Here's a Google Earth image of it, kind of at an angle, and you can see, again, it covers all of those areas, but it looks pretty flat. You don't really see a hole in the ground. Like I said, it's filled in. There's no crater there. As a matter of fact, if you go down on the land surface, that's one of the flattest areas in the state of Iowa. I call it this is what I call my scenic overview of the crater, and this is about all you'll see if you go out there to see it. And the reason it's so flat up here is because it's in the area that was most recently glaciated. That gray area on the map there is a Des Moines lobe. That's the path of the last glacier that came into Iowa. It only left about 12,000 years ago, so the rivers haven't had time to really dissect too much. But the crater is just below the land surface, just below this glacial till here. We first learned about it when the town of Manson decided to drill their first water well in 1905. We didn't have any geologists around there yet then, but in 1912, a geologist from the survey named Norton went up to the town and visited with the people, and this is a report he made. He said that they encountered no rock of any kind to a depth of 1,050 feet. On the left is kind of a little illustrated log of what they came through there. And once they got to the bottom, water flowed in immense volume, so that's pretty weird. They didn't know exactly what was going on. It certainly didn't fit our understanding of what the geology was at the time. As a matter of fact, Norton said it would literally construe this to revolutionize our current concept of deep geology in the region. So the other little illustration I put up on the left here is what we would expect to see at that kind of a distance. A glacial till on top, just as we saw it at Manson. But then we went into the Dakota sandstone and Cherokee, Pennsylvania, and in through all of these limestones and dolomites and sandstones. We don't have any of that. All we have is this kind of shaly, dirty material. So what's going on there? Then on top of that, at the very bottom, the people of Manson reported that they hit granite. Well, granite is the basement rock. It underlies all of these sedimentary rocks in Iowa, and the basement ought to really be down about 10,000 feet or more here, and there it is up a little over 1,000 feet. So something definitely unusual going on here. Not only that, when they looked at the water quality that they were able to produce, they found it was quite different than all the other wells around the area. Here's a average of the deep nine deep wells kind of in that area in Manson and a few of the chemistry of the thing. The Manson well is a little higher in sodium potassium than most, but it's incredibly higher in chlorine than most of the wells that we have in the area, any of the wells that we have in the area, as a matter of fact. Then if we look at some other things, calcium, magnesium, bicarbonate, sulfate, these are all the things that make water hard. And you notice how high they are at all of these other wells and not at the Manson well. So Manson is the only naturally occurring soft water out of the bedrock that we have anywhere in the state of Iowa. So that's pretty unique. Again, there's something weird going on there. Just what? Well, in 1953, the U.S. Geological Survey, which has a branch, a water branch in Iowa City, and the Iowa Survey, the IGS, got together with a joint investigation. They went out and drilled a couple of cores. Now, this is a drill rig they use. It's sort of pretty archaic by today's standards, but it managed to drill a hole. And what a core is, it's a cylinder of rock that you recover from the ground rather than just little bits and pieces as the normal drill bit would grind them up. So the cores are a lot better because they show us exactly what we have. Well, their first well encountered this strange material, and we call it a clay-rich sedimentary class breccia. A breccia is a rock made up of a lot of broken pieces of other rocks. Sedimentary class means that all those broken pieces are sedimentary rocks, and clay-rich kind of describes the matrix around them. So we had a clay-like material that was full of all these weird rocks. So that's totally unusual. Well, this sample here was taken from 326 feet, and shortly later, just a little below that, the drill hole caved in, and they lost that hole. And so they moved over about a mile and drilled another hole. And at only 129 feet, they ran into this other type of breccia, and we call it a crystalline-clast breccia. A breccia, again, broken up rocks, but these are all crystalline-clast, granites and gneisses and rocks that you expect to see either in the Rocky Mountains or way deep here. And here it is 129 feet below the surface. Pretty unusual. Well, they were able to continue down a little farther with this hole. It got down to 407 feet, and they got into bigger pieces of rocks and more solid rocks. And, you know, if you looked at this, you wouldn't think this was any different than any other kind of granite or gneiss that you would expect to find at a depth of 5,000 feet or something like that in Iowa. But here it is right here at the surface. So the initial interpretation was, oh, maybe we have a volcano. Don't worry, Blandon. Blandon was this little town that's not around anymore, but it was closer to the center than Manson. So don't worry, Manson, Blandon. You're on top of an ancient volcano, but it hasn't erupted in 100 million years. Well, they had the age about right on it. Then in 1955, a University of Iowa graduate student, Jim Dryden, decided to study that crater and the core material that came out of it. So what he did is he looked at a series of other wells in the area, made a little cross section, and this little index map on a map shows these individual wells that he looked at information from, and then the two cores are yellow in the center. And then there's a big cross section that I drew, and you can kind of see the types of materials that these wells encountered. Disturbed area, this is that shaly material. He ended up calling this a cryptovolcanic structure. At the time, 55, they didn't really know too much about meteor craters, but so this was what they thought, a cryptovolcanic, which is a giant gas explosion coming out of the ground, not really a magma ejection, not really a volcano like we like to think, but just a big explosion in the ground. We do get a few of those, but nothing anywhere near this big. So here's how the cores fit into his model. This green area that he calls disturbed area was this shaly material, and then the crystalline rocks were right toward the center of the structure. So this was his interpretation of it. And he also drew the first map that we actually have, the limits of the crater, kind of an oblong shaped thing. Not too bad though, not too bad. The next bit of information we got to understand this crater was done by a professor at the University of Houston named Nicholas Short, and he studied impact structures and other things like that. And he got a sample of the Iowa rock, and he cut a thin section of it. Now, a thin section is when you cut a real thin piece of rock, glue it to a microscope slide, grind it down so it's thinner than a human hair, so that light can actually pass through it, and then you can see a lot about the characteristics of the rock. So this is the Manson rock that he looked at here, and what you see in that yellow area is quartz grains. Normally when we see quartz under a microscope like this, it looks very much like this illustration in the corner here, kind of plain, not much going on, but this match, the Manson Impact thing, showed these lines, and these turn out to be called parallel deformation features. They're deformed by the impact, so the quartz is actually deformed by the impact. And when you see multiple intersecting sets of those, like we see here, a set of blue ones going one direction, yellow going the other, that is considered now by geologists to be definitive evidence of a meteor impact. What really happens there, there's such a big explosion when that meteorite hits that the shock wave actually deforms the quartz grains, slides individual pieces of the quartz along crystallographic axis with such pressure that it actually melts them. So we have little lines of melted glass in the middle of this quartz. They're especially visible here in Manson because right after the impact, some hot fluids move through, dissolve the glass and left behind a series of little bubbles. These little bubbles make the lines look darker. They're called decorations, and they're fluid inclusions, so we could actually tell a little bit about the chemistry of the water that was moving through this right after the impact. Pretty interesting stuff. Anyway, here's why a shocked quartz like that is definitive evidence of an impact. In this little chart here, we see temperature on a kind of logarithmic scale going up on the left, and then a horizontal scale is pressure. The green field there shows all the possible temperatures and pressures that's possible anywhere near the Earth. In other words, you get any higher pressure that knows it's going to blow out and you don't see any pressure anymore, any higher temperatures and it's going to melt. So that's where you see things on Earth. Now, over here on the right, you see parallel deformation features. It's a whole order of magnitude, 10 times greater than what is possible from just a volcanic explosion or something like that. So that's why we know that's definitive evidence. Well, in 1969, Iowa produced another geologic map, and by that time, the idea of this being an impact crater was around, but they didn't really believe it, and they thought this was the shape, so they're getting a little closer to rounded, but rather than an impact structure, they called this thing the Manson anomalous area. Who knows what it is? They also, on this map, mapped a little area of Precambrian crystalline rocks in the center. Those are those crystalline rock breccias that we saw in the drilling of that second core hole. Then in the 80s, along came these two guys, Louis and Walter Alvarez. They're both professors at the University of California at Berkeley. Louis Alvarez, a Nobel laureate physicist, and his son Walter on the right there was a geologist. Walter decided he was going to try to figure out what was going on at that period of time. And so he looked at this little layer here that we call the Cretaceous Paleogene boundary. It's the boundary between two geologic units, and it's frequently marked by some sort of a weird geologic layer. In this case, it's a layer of shale, and it's called the KP boundary. That's the boundary between the Cretaceous and the Paleogene. You couldn't use a C here for Cretaceous because the Cambrian is an older unit, already has the C for an abbreviation. So Cretaceous uses K. So that's a KP boundary. If you look a little closer at it, what we see is limestone below and limestone above, and then here's a little thin layer of clay with nothing but a few fish fossils in it. So what the heck is going on there? Something happened that turned off the whole mechanism that was producing limestone for a period of time, and then turned it back on later, and we got similar type of limestone above. So what was going on in there? Well, one thing that went on there is that was one of the big extinction events in Earth history, including the extinction of the dinosaurs. 90% of all marine species died out at that time. 70% of all terrestrial species died out at that time. And Walter was trying to understand a little more about that by trying to figure out what period of time was involved in that. And his father had an idea. He said, iridium, that's the answer to our problems. Well, what the heck's iridium? Iridium is a platinum group element that's really rare on Earth. Earth rocks contain on average about 1 to 2 parts per billion of iridium. And the sedimentary rocks, like the kind they're looking at here, usually have 0.05 parts per billion. Not very much at all. But these chondrite meteorites that come in, they have as much as 500 parts per billion, much richer in that. So Walter's idea, or Lewis's idea, was we'll look at the amount of iridium in this clay, and we'll be able to tell how long a period of time these little micrometeorites that were coming in. The Earth is constantly bombarded by these micrometeorites, so they were carrying a kind of a background level of iridium in. And he said, we'll look at how much iridium is in this layer, and we'll be able to tell how long the time was. So they did look at that, and what they found out was there is 10 to 60 times more iridium than could possibly be explained by normal normal aggregation of this iridium through those micrometeorites. So something else must have happened. So what they said happened was a big meteorite came in, and they wrote this paper, an extraterrestrial cause for the Cretaceous tertiary extinction. They postulated that there was about 200,000 tons of iridium, all told, all over the Earth, if you looked at the amount that they saw in their samples and considered that was distributed fairly easily or uniformly across the Earth. So what could have brought in that much iridium in a relatively short period of time? Well, they said an asteroid 4 to 9 miles in diameter would have that much iridium. So they think we were hit by a big asteroid at that time. And an asteroid going 45,000 miles per hour, which is kind of the average speed, would have blown a crater 125 miles in diameter. Big crater. Not only that, they said that material that would be blown into the atmosphere, the dust and stuff, would have blocked off the light of the sun for 2 years. So for 2 years, the maximum light would have been about 10% the light of a full moon. This is the idea that with the light blocked off, the trees and the vegetation would die, and the plants that ate the vegetation would die, and the animals that ate those animals would die. So you got a chain reaction, and you got all these things becoming extinct. Well, this was actually the idea that finally led to thinking that maybe if we shoot off all our nuclear weapons at one time, we'll do the same thing and kill off everybody. So that was the idea of nuclear winter. Originally came from this thinking about what killed off the dinosaurs. And of course, that thought of a nuclear winter finally got us a nuclear test ban and a little more security. So where is this crater at? This is a map that shows dots that indicate where the known impact craters are, and there are none that are really big enough in the correct age. So what happened? Was the crater destroyed or not yet discovered? Maybe it was an impact in an ocean, we just don't see it. Or maybe there were a lot of small impact craters. Well, the scientists continued to look at these things, and they looked at another exposure of that boundary. This one is in southern Colorado, and it was in when the meteorite hit. This was a land area rather than sea, and so we got a little different look at the thing. So this is what we have: the Cretaceous rock below, the Paleogene above. There's a coal below, or a coal above, I mean, and a shale below. So here's the boundary. These two little colored lines here, the white and the orange. The white is what we call the ejecta layer, and the orange turns out to be what we call a fallout layer. So I'll get a little closer look at this thing. Here we see them again, the ejecta layer in orange and the fallout layer, or I mean, in a whitish color, the fallout layer in a little more orange. So what are these things? Well, the ejecta layer is basically a big splash of molten rock that came out of this crater and covered much of North America. You can just imagine a big splash of molten rock coming down. That certainly wouldn't have been good for the dinosaurs or anything else around. The upper layer there is called the fallout layer, and that's what happens when all of that debris that's in the sky blocking out the sun comes falling back down to Earth, like a lot of little micrometeorites. And so you would have seen all of these little trails of particles of sand and stuff like that coming in through the atmosphere. And just like a meteorite, when they fall, they would heat up. And so what scientists postulate is that would have heated up the atmosphere to 2,700 degrees, which would have set anything that's volatile on Earth on fire. And sure enough, we do see evidence that maybe as much as 70% or more of everything vegetation on Earth at that time was burned up. So that would have been a very bad time to be around. At that same location out there in Colorado, one of the scientists found quartz. They found shocked quartz. Well, shocked quartz, remember, is an indication of a meteor impact. So that right away said that that was a meteor impact, and it kind of proved their idea that a meteorite might have caused all the dinosaur extinctions. Not only that, if there's quartz at that environment, that gives you a little clue on where the meteor crater would have been. If we look at the Earth's crust, we see it's basically composed of two major rock types. The crustal rocks, oceanic rocks, are shown in blue on the map here, and the continental rocks in red. Well, quartz is restricted to the continental rocks. You don't get that in oceanic rocks. And so the impact site must have been somewhere on a continent. So that narrowed it down a little bit. Quartz on the continent, no quartz in the ocean. So he got to looking at all of the places where they've looked at that KT boundary. So these or yellow dots indicate places where the boundary has been sampled. And they looked at the largest size of quartz grains they could find at any of those sites. The idea being that the larger grains would have fallen closer to the site of impact. And sure enough, the largest grains turned out to be right here in the Colorado-New Mexico line, very close to Manson again. Well, as it turns out, Manson was not the site that killed the dinosaurs. Chicxulub was down here in Mexico, but you see, they're both about equal distance from that site in Colorado. My next big advance in understanding the crater was when I took my little crater talk to a National Geological meeting in Denver. And while I was there, a person from Amico Production came up to me and he said, "We have a seismic line across that crater. I bet you'd like that." And I sure did. So this is what the seismic line looks like. Now, a seismic line is a bit of information where they have a machine that puts sound waves into the ground. They're reflected off various geologic units back to microphones on the surface. And with a lot of computer processing, you can kind of get a look at where these reflectors are. So this is a cross section from basically the center of the crater outward, and all these little reflectors, if we interpret them, were pretty easy to interpret actually. On the far right side of this, you can see what the geology looked like before the impact. So this is the area not affected. the area to the right or the east of this limit of disturbed strata. You see Paleozoic, these are the limestones and sandstones and rocks that we're used to looking at around Iowa. And below that are what called Proterozoic clastics. This is a deep clastic basin. Clastics are sand and gravel and silt and clay and things like that deposited by rivers. And so this big clastic basin is related to the Mid-Continent Rift, which is a big Precambrian fracture that's off further east yet. And then finally down the very bottom there, we see these Proterozoic crystal rocks. You always get a big dark reflector like indicated by the red line here when you get a big change in rock types like from the clastics to the crystalline rocks. So we can see that in normal geology, and if we move to the west, we start to all of a sudden get the inside of this disturbed area where all of those features kind of go up and down, get thinner and thicker, and we start to get Cretaceous marine strata preserved in there. A little farther yet, we get to that kind of a curve-shaped thing where you get totally disrupted strata, and all that stuff disappears entirely. Plus, the Precambrian basement comes right up to the surface, so we got that central uplifted block. So what this seismic line told me is that we had a classic complex impact structure. This is what it would look like if I continued the seismic line to the west and we could see the whole crater. This would be the interpretation. Now, what's a complex impact crater? Well, here's a simple impact crater. It's just a big hole in the ground. This is Behringer Crater in Winslow, Arizona, and I'm sure that many of you have been out there to see that crater. It's pretty impressive. It's almost a mile across. But when you get bigger craters like Manson, you get an excavation crater like that meteor crater blown in the ground, but the crater continues to grow, and with the pressure pushes up the outside edges of the crater, lifts them up, and then when that pressure is released, those outside edges fall back down, and as they fall, they push up the center of the crater, giving you that central uplift. The physics is pretty much like a drop of water falling in a puddle. You know, you've seen a drop of water falling in a puddle, and sometimes it pops up a little central peak like that. Well, these rocks weren't really fluid, but they were behaving as fluid because they had so darn much energy in them. So here's a crater on the moon that's about the same size as the Manson crater. This is about 22 miles in diameter. And if you look at around the outside, you've got what we call the terrace terrain. This is that area that was uplifted and dropped down, all jumbled and broken up rocks. In the center, there's an area of a central peak, and then the area in between that we call the crater moat. If you got an impact like this on dry land, that area in between that uplifted peak and the terrace terrain would normally fill with water, so you'd have like a castle in the middle with a moat around it. So that's why we call it the crater moat. So this is a crater about the same size and shape as Manson. Off to the left here, you see a little bitty crater. This is a crater that's about the same size as Meteor Crater. So if you've seen Meteor Crater, there's the size of Meteor Crater. The red outline's the size of Manson, quite a bit bigger. Well, once we got that kind of information, we went back and looked at all of the water wells that we had in that area that went into bedrock, and we said, what can this tell us about the crater's shape? And we ended up mapping a pretty circular crater, which is pretty much what we have today. So we have a crater at Manson. Is it the right age? Well, we knew it's about the right age. The age between the Cretaceous Paleogene boundary is about 65.5 million years. So what do we have at Manson? We have 100 million year old rock that was blasted, so the Manson crater has to be older than 100, but the stuff on top of it after erosion is Pleistocene till, and that's only like 2.5 million years old. So somewhere between 100 million and 2.5 million, that crater was blown. Well, looky there, the 65.5 fits very conveniently inside of there. So maybe we had a Manson crater. Well, geologists, of course, were always looking at that period of time anyway for where was the crater that killed the dinosaurs? How did that work? I want to know more about it. And so got some geologists at the U.S. Geological Survey to look at some of the samples that we collected from Manson. And they tried to do an age date on it. So this is one of the early age dates. And this is using the decay of uranium, looking at daughter and mother products to see how old the rock is. And they came up with an age of 65.7. And they said that age is indistinguishable from recent estimates of the age of the KP boundary. So maybe this was one of a number of little impacts that occurred at that time. Well, we're pretty lucky because we have a connection here at the University of Iowa to Gene Shoemaker, who was one of the most famous geologists and astroscientists ever, really. And he used to come around to visit his daughter, who taught at the University of Iowa. So we got to know him, and we got working with him to see if he could shake a little money loose from the U.S. Geological Survey, which they did. And we got a cooperative drilling program, the U.S. Geological Survey and the Iowa Survey, to drill a bunch of holes in that structure to find out some more information about it. The main project goals were to kind of get a more accurate age determination, find a little better rock to date, to identify the type of impactor. Was it a comet? Was it an asteroid? Was it a stony or an iron meteorite? And then finally to compare the target rocks at the KP boundary. In other words, what are the rocks that are actually thrown out of the crater there, and how do they compare to the little chips of rocks that are found at these exposure sites all around the world? There was material blown out of the crater that landed at these other sites. Is it compatible with what we see here? So we drilled a series of holes. We drilled 11 holes altogether. They're shown in yellow here. The two earlier ones that the USGS drilled are shown in red. So we drilled all these yellow ones, mostly along that seismic line, so we could better understand the seismic line and get an idea of what we were drilling for. We got over 3,000 feet of drill core out of that. And what we ended up with was this, shown by this little cartoon, of the type of impact rocks that we found. Central Peak has 4 different types of impact rocks on it, and then the terrace terrain has got one type, and then another type, a 6th type, covers everything. So how did these get here? Well, when the impact exploded, it blew a hole, boom, and created a crater floor, which was melted. The most energy was right there, so the most heat and pressure is right at the crater floor, and it decreases going down. So the rocks that are the shallowest there are the ones that had the most energy on them. So the Crystalline-Clast Breccia with melt matrix, we'll talk about these a little more, was a crater floor, basically a mostly melted rock. Go down a little deeper, you get rocks that are not all melted, but are mostly just broken up into a lot of little pieces. And lower than that, we get big chunks of this basement rock, the crystalline rocks, granites, and gneisses from way, way down there that are just pushed up on the central peak. So those are the types of rocks that we see there. The overturned sedimentary strata is on the terrace terrain there, and then when the central area was lifted up as the terrace area collapsed, somehow this Keweenawan shale breccia got on top of there, and then the Phanerozoic clast breccia covered everything. Well, there we go. So what are all these things, and what the heck was going on? We'll run through these things, and although the actual percentage of looks more like this on the central peak, there's almost all crystalline megablocks, which is a thin skin of those other units. But let's start out by looking at the deepest lying rocks, these Proterozoic megacrystalline blocks. Here's what our drill core showed. It looks like normal granites and gneisses, the kind of things you normally find at the basement. The core's in the box on the right, and a couple of little close-up ones on the left there. If we cut a thin section of this and look at it, we see it's just the quartz are just loaded with all of these shock features, parallel deformation features. It's definitely quartz, and it's definitely shocked, and every single quartz grain in there is shocked, and the other grains are all messed up too. Well, coming up a little shallower, we're getting area that had a little more energy, and so those big blocks were more broken up into a lot of little pieces like this, with big blocks of granite, with blocks of granites and gneisses mixed in with a lot of smaller ones. So this is what we got as we went a little higher, and we looked at it in this section. You can see more broken up grains, and again, every one of these things show shock features. Those brownish colored lines that you see are shock features in quartz. So every one of those shock grain quartz, every one of those quartz grains is shocked, and some of the other minerals like that hornblende, which is the green mineral that you see there, is also, you can see, busted up and shocked. So everything's shocked and broken up in there. Go a little higher now, we're getting up toward the crater floor where there's a lot of heat and a lot of pressure, and so a lot of these things melted. And in fact, that's what we see. We see mostly this dark colored material, which is glassy material, with a few big pieces that either didn't quite melt yet or recrystallized. Now, those recrystallized ones were one of the things we were looking for to date. We look at one of these in the microscope in thin section, and you see these swirly patterns. You can see this stuff was melted. Lightish colored things were quartz grains that were melted and stretched and deformed. You see a few white crystals there, kind of white areas, that those are recrystallized grains. And then kind of in the upper right there, you see a grain that has a lot of little cracks on it. That's a shocked quartz grain that didn't get entirely melted. You can see the fractures, though, that got melted, and the white rim around the outside of it was melted. So you see a little bit of everything, but these rocks are really totally messed up. But one of the things we did see there is sanidine, and sanidine is a feldspar that recrystallized after the impact. And the secret of that is, since it's recrystallized, it's basically let loose all of the radioactive gases and stuff that were formed as uranium decayed after the rock was originally formed, and resealed it again. So it essentially reset the clock on the age dating. So this is exactly the material they were looking for to get an age date out of it, and they did. We'll talk about that later. The uppermost unit on this central peak here is the Keweenawan Shale-Clast Breccia. What in the heck is that? This is what it looks like. It's mostly shale. Keweenawan is the age of these shales, because we see these up and around Lake Superior. We see them deep in the Iowa subsurface. Shale-Clast Breccia. Breccia, broken up pieces of shale. That's mixed with a bunch of light colored materials. The whiter colored materials you see there are actually melted shales. We've got melted and unmelted shale all mixed together and sitting on top of the central peak. Well, this is our biggest mystery. What the heck is this? Where did it come from? How did it get up there? Show you what we know about it. This was what the geology looked like before the impact. You see that Keweenawan clastic basin getting deeper to the right as we go toward the mid-continent rift. So there's a Keweenawan clastic rock, and toward the bottom of it is the shale unit. It's right near the bottom of that clastic sequence. So the impact happened here where the red arrow is, blew everything out within that hemisphere there. So there was certainly nothing but crystalline basement rocks at the bottom when the central peak came up. So what happened is you blew a big hole in the ground like this. The central peak popped up when the sides dropped down, and then somehow this Keweenawan shale, which should be off to the side over there, appears on top of this thing. So I'm not sure exactly how it got there. It's got squeezed out or something when the edges of the crater were collapsing. That's a big unanswered question right now. Okay, the Phanerozoic-class breccia covers everything, and this was a kind of unusual unit. This is what we got there. Phanerozoic, these are rocks that were existing there before the impact, before the crater. And so the class, the pieces of the broken up breccia rock, are made of these Phanerozoic pieces. There's limestones and shales and sandstones and all kinds of rocks like that. This is what it looks like. Well, we looked at the percentage of the large class that we found in this, and we found they were dominated by Cretaceous, which was the shallowest unit. The little bar that you see in the middle there shows the Manson wells that we were looking at. The Cretaceous is at the top, colored green. It's the thinnest unit. Below that is the Paleozoics. These are all the limestones and shales and those kind of things. A little thicker, more deeply buried. Below that are the red clastics in yellow, and then the crystalline rocks in red. And you see the thicknesses are kind of proportional to what you see on that illustration there. And yet what we actually found in the rock was inversely proportional. The shallowest ones were by far the most representative. And if you look at the little pie diagram, almost all of it is green. Most of it is Cretaceous rock. And then a large portion of what's left was the Paleozoic rock, which lie underneath that. The red clastic, which was much more volumetric in the hole than anything else, only appears in a little area, a little bit there, and a very few crystalline class. So what in the world is this material? So we started looking around at other impact structures to see if someone somewhere else had reported anything like that. And we looked at the Reese crater in Germany, and they have a material called the Bunte breccia there that has pretty similar proportions. Now, these are different materials, different depths and everything, but I've kind of color-coded them so that they match the Manson ones, and you can see it in a comparison. The shallowest rocks, the Upper Jurassic rocks at Reese are proportionally about the same as Cretaceous in Iowa. The next lower ones in the Upper Triassic, or the Upper Jurassic, I mean, are about the same as our Paleozoic, and so on down. So our rock looks a lot like this Bunte Breccia. Well, what the heck is the Bunte Breccia? That's what they call a surge deposit. From the actual impact blast, the blast energy goes ripping across the landscape, tearing up the landscape that is there, the rocks that are there, and mixing them with rocks that are thrown out of the crater, and all this stuff gets mixed together and blown out of the crater. So if you look at the Bunte Breccia in the Reese crater, I've colored it yellow here, you can see it's on the very outside edges of the crater in these down-drop terrace terrain, but it's totally blown out of the center of the crater. This is what you'd expect if that's where it came from, out of the center. But at Manson, we find that the equivalent Phanerozoic-Clast Breccia actually covers everything, including the central uplifted peak. So it's a little weirder, but it did tell us what we have. We have what's called a resurge deposit. That material was blown out of the crater originally and then carried back in. So what happened is we had an impact at a shallow sea, and the sea that was close to the crater got vaporized or forced back by the energy. This ground surge came along, tore up the landscape, deposited all that material like that. So there's the ground surge deposited just like the Reese Bunte Breccia. But then we had the sea come roaring back in and pick up all of that unconsolidated material, or a lot of it anyway, carry it back into the crater, fill up the crater, and we ended up with something like this. Well, we see other craters with resurge deposits. What happened was period of erosion took that resurge material that was outside of the crater, eroded it away, and just preserved a little bit on the down drop blocks and in the center of the crater, with a little bit of the central peak poking through in the center, if you notice there. So we see this other places. Like I said, a good example of this is the biggest impact structure in the United States, the Chesapeake Bay crater, which is right there in Chesapeake Bay. If you look, they have a unit that's called the Exmoor Breccia that is their resurge deposit, and boy, it looks exactly like the Manson Phanerozoic-Clast Breccia. They look exactly alike, and they formed exactly the same way. So that's in fact what we have there, is a resurge deposit came surging in, and it covered up everything. And the erosion has left most of that covered up. You can see the yellow. The squares and the dots here represent wells, both drilled water well type samples and cores that were drilled. And you can see most of them go into that Phanerozoic-Clast Breccia. There's just a few of them colored in yellow, or areas where that resurge deposit was totally eroded away. So basically, underneath that material that came flowing back into the crater, we have a pretty pristine, very little eroded impact crater. Well, the last of these units that we had, an impact unit, was the overturned sedimentary strata. And this is, again, not uncommon in some impacts. And what we had when we drilled our well number 4 there on the terrace terrain, as we went through the Pleistocene till, we went through that resurge deposit, and the first rock unit we hit below that was the Proterozoic red clastics. So these are those red clastics down there. They're 1 billion years old. 1,000 MA, million years. MA stands for million years. So 1,000 million years, 1 billion years old. Below them, the drill went into Cambrian. We got Cambrian rocks over 500 million years old. Below that, Ordovician rocks, 450 million years old. And finally, the drill bit, as deep as we could go, at over 1,200 feet, was in Devonian age rocks. So what's wrong with this? If you're a geologist, you know the law of superposition says that the oldest rocks should be on the bottom, not on the top. So something happened that flipped this whole sequence over. And that's the overturned sedimentary strata. So as this crater formed, rocks were being thrown out of the crater on the side there. with the last gasp of energy, some rocks got thrown out and then collapsed back down onto the surface like that. So you've got an inverted stratigraphy, and that's what we drilled through for the M4 core. If we only would have had a little bigger drilling machine, we could have gone a little deeper. We would have actually seen that impact surface, and that's what I would have liked to see. That would be my #1 target if we're going to try to drill again. So there's what we ended up with, the Manson Impact structure. Pretty interesting. It was an impact at the time when there was a ocean basin covering part or maybe all of Iowa. We're not really sure. It's called the Western Interior Basin. It actually connected the Arctic Ocean in the north with the Caribbean Sea on the south, and then up through Hudson Bay to the Atlantic Ocean. So there was a sea there at the time, and the meteorite came in, hit right in that area there. And so that's where the sea got pushed away and the Resurge deposit came in. It's interesting to look at the history of what happened after the impact. So this is what's called the zero edge of the Cretaceous. Now, there were Cretaceous age rocks that were covering the whole state, and they got eroded back about this far. So if we look at the stratigraphy inside of the crater itself, one of the wells on the down-drop blocks actually preserved this old strata that was originally there. And we could see we had not only the Dakota Formation, the Graneros, the Greenhorn, and the Carlisle, which are the units that we see in Iowa today, but we also had Niobrara and the Pier Formation on top to some degree. So basically the Paleozoic strata were there. We got Mesozoic strata deposited based on that well, we know, up into at least the pier. And then boom, there was the impact. It blasted a hole through everything, pushed up a central peak like that. And by looking at wells and exposures west of Iowa, we can see what kind of units were deposited out there and how they were thinning as they moved into Iowa. So we can get a feeling for how thick they were in Iowa. And I apologize for not having changed all of the meters to feet in this one, but I just didn't get around to it. So after the impact, there was about 130 meters of Cretaceous shale deposited. Above that, about 35 meters of the Fox Hills Formation. And above that, 25 meters of the Hell Creek. These are the famous dinosaur beds, the Hell Creek and the Fox Hills out west. And we had our share of dinosaurs here too, I'm sure. Then there's the actual KT boundary. So all the dinosaurs are dead beyond this point. Then we got a little more deposition of some Paleocene strata and a little Miocene strata. About 800 feet total of material on top of the impact site. Well, this material all eventually got eroded away, as did all of the other material that we had. And it took it right down to what we see today. Then the glaciers came in, buried everything, and left a little layer of glacial till. So this is what we see today, the crater just covered by glacial till. So that told us a lot about it. Just exactly how old is that structure anyway? Well, like I said, we found some sanidine there, and Glenn Izett from the U.S. Geological Survey dated that sanidine. And what he found out was that using Argon 4039 dating, which is looking at uranium decay again, he found that 12 analyses yield an average mean age of 73.8 million years. So in other words, it's not the same age as the Cretaceous Paleogene boundary. As a matter of fact, it's about 9 million years older. On top of that, he said that the extraterrestrial object must have struck in an area that was covered by the Western Interior Seaway. Well, we just saw that illustration that I did. And coincidentally, he had been working with some other people out west to date some of the volcanic rocks that were erupted about this same time, and the ashes fell down in the Cretaceous Seaway. So if we look at what he had volcanic ashes dated in the Crow Creek unit that were 73.7 plus or minus 0.45, as opposed to the Manson age of 73.8 plus or minus 0.79. So anyway, these are essentially the same age. So out in the Crow Creek unit of the Pier Shale, he found material that was ejected out of the Manson crater. A little more accurate age dating later, they came in with a final age, which is the current accepted age for this Manson impact of 74.1 million years. Again, about 9 million years before the dinosaurs all died off. I always tell people that we killed an awful lot of the dinosaurs with this impact, but we didn't quite get them all. And so they managed to come back. Well, of course, being curious, we had to go out to that site and actually look at what the material ejected from Manson would look like. Well, again, here's the Manson crater and the zero edge. The Manson crater would have exploded, thrown debris over an area like this, and then subsequent erosion eroded it back to there. So here's where the Crow Creek is now. That's how far all the materials that were Manson ejecta east of that have been eroded away. But if we go out there and look at the Crow Creek and we look at Yankton, South Dakota, we can actually find this. And there is some Crow Creek limestone. We went out here several times over a period of about 2 years, and we actually hammered with our little rock hammers and our sledgehammers, hammered this hole down through that entire Crow Creek unit and sampled it all up and down to look at where is the Manson ejecta. Do we really see it? And sure enough, here's a shocked quartz grain. Looks a little different than the ones we saw at Manson because it didn't have that hydrothermal pulse that makes these shock features look a lot stronger. But those are all shock features in there. That's a piece of Manson quartz. Not only that, we found other things. We found Paleozoic dolomite and Paleozoic glauconite. These are very soft rocks that would never have eroded and been carried out into the middle of the ocean under normal geologic processes. So they had to be thrown out into the ocean. So that's good. We have more proof that in fact is a Manson ejecta layer. Well, we didn't kill all the dinosaurs. We were responsible for any extinction. Scientists took a look at the excuse me, at the vertebrate fossils that were around at that time. And they found out, yes, there were a few things that went extinct about that time period, their time period of the Crow Creek and the Manson impact. The hadrosaurs became extinct about that time. These pachycephalopods, these weird dinosaurs with the big skull caps, they went extinct about that time. These giant Cretaceous Deinosuchid crocodiles went extinct about that time. And a lot of these centrosaurs became extinct. Not all of them, but a lot of them. So there were a lot of things that became extinct about that time, but it wasn't related to the impact. Well, the scientists that studied these things said that, the normal extinction that we have with animals through time, this is pretty much normal. So no, they couldn't say for sure that any of these impacts were directly related to the Manson structure. A little later, a fella came along, Mike Rampino at New York University, and he put together a little graph looking at craters all over the world and comparing the crater diameter to the number of species that became extinct, the percent of the species that became extinct. So here's Manson right here at 37 kilometers in diameter. So according to his chart, somewhere between 8 and 30% of animals that were around should have been driven to extinction by a blast this size. But we haven't seen anything yet that we can definitely say were caused by extinctions that were caused by that impact. But according to Rampino, there should be. So maybe yes. We have yet to figure that out. What would be the effects of the Manson impact if it were to occur today? Well, to figure that out, we took a look at the biggest blast that we've seen since scientists have been studying these things. And this was a meteor that exploded over Russia on June 30th of 1908 called the Tunguska blast. This was an air blast. It actually exploded in the air, didn't make it to the ground, but the effects are very similar. And this was a pretty good sized blast. It blew trees over in an area that they mapped out quite large like that. And from these sort of things, they estimated the explosion was somewhere between 10 and 42,000 kilotons of energy. Well, that compares sort of to the atomic bombs we dropped on Japan that were 13,000 and 22,000. So it's in the kind of the same range as those Japanese nuclear bombs. Well, how does that work for Manson? Well, Manson, we estimated, is about 5.5 billion kilotons. So that's like 200,000 to 500,000 times greater than the blast at Tunguska. But that's all we have for a comparison. So we kind of scaled that up to get an idea what would happen if the Manson impact occurred today. There's the Manson crater, that little red dot there. The blast the release of 500 billion kilotons of energy. You can imagine that giant meteorite, all the kinetic energy it had, all of a sudden hitting Earth and stopping. All that energy be released. A lot of energy, man. That would have set everything within this yellow circle on fire. The shock wave, the electromagnetic pulse would have. So most of Iowa would have been set on fire by the shock wave. The blast would have blown trees over, compared with what the Tunguska blast did. Would have blown trees over as far away as Chicago, St. Louis, Ogallala, Duluth. And there was a trader who was riding in the forests of Siberia at that time who was knocked unconscious off his horse by the shock wave. So if we scale that up, we'd have people being knocked unconscious in Pittsburgh, Atlanta, Albuquerque, Salt Lake City. So you don't have to get a lot closer than that to actually kill people. So I guess that about most of the population between a circle between Columbus, Ohio and Denver, Colorado would have been killed. So most of the people inside of that circle would be killed if that happened today. Well, it's kind of interesting. There's a thing online called the Impact Effects Calculator. Here's the URL of it. I can put it back up if you're interested in checking it out in the future. But what it allows you to do is input things like the size of your crater, what kind of rocks it crashed into, angle that it came in, all of that kind of information, and project what the effects would be at some distance from that impact. So I took a look to see what the effects would be if that impact occurred at Manson again. What would it look like in North Liberty? And these are the effects here. The air pressure blast would have arrived about 758 seconds after the impact. So about 12 minutes after the impact, we would have got this big shock wave. It would have come in at a pressure of about 11.6 pounds per square inch. Well, what does that mean? Well, see on this chart, 10 pounds per square inch, most combustible material will ignite. 12 pounds per square inch, we'd expect 98% fatalities amongst people in that area, with the other 2% badly injured. So that would kill most people in this area if that happened today. Well, there would have been maximum wind velocities of about 330 miles an hour here in North Liberty. Holy cow. Shock wave would have been 98 decibels. That's like standing in front of the speakers at a rock concert. Multi-story buildings would have been collapsed. Wood frame buildings would have been collapsed and burned. Glass windows would shatter everywhere. 90% of the trees would be blown down, with anything that remained would be stripped of all its leaves. So that would have been a pretty nasty deal. So we take another look at it. This aerial photo here shows the building where we would normally be meeting in, there in North Liberty, right about there. And if we zoom back a ways, there it is. Well, the meteor would have come in, boom, and would set right down on North Liberty. Here's what that meteorite would look like sitting on North Liberty. See, it goes all the way north to Scales Benz Road, south to the grade school there, clear over to the Pelling asphalt company there along the road out to the freeway. It would have been pretty big sitting there. But of course, it didn't sit there. At 100 trillion tons weight, going 45,000 miles an hour, the kinetic energy there is just tremendous. You can imagine. And if all of that kinetic energy is released when it stops, that's going to be the 5.5 billion kilotons of TNT energy. So boom, that thing would have gone off. Now here's a little bigger map, a highway map, and you see the black dot there on North Liberty. That's the meteorite sitting there in the ground. The blast would have vaporized everything within that circle. So all of North Liberty and up to the Coralville Reservoir would have been vaporized, with the vapors blown high into the stratosphere. Everything inside this circle would be melted. So we're clear down into past Oakdale, down to the freeway, clear up to almost to Shoeyville. All this material would have been melted and thrown out of the crater. This material here would have been pulverized into little small pieces of rock and blown basically anywhere on Earth. So that takes us all the way. It takes care of most of Iowa City and takes us almost out to Oxford. And then this is the area that would have been uplifted and then dropped down to form the margin of the craters. This would have all been totally destroyed here. So we've got the crater sitting here would have been all the way up to Hiawatha, clear down to Lone Tree, out beyond Springville, out beyond Amana Colony, almost to Maringo. Holy cow, that'd have been a pretty big crater. We don't see that there, fortunately. Well, I said there's the Manson crater, and here's the Chicxulub crater. This is actually the crater that did destroy the dinosaurs. Bill Bryson wrote this very interesting book, A Short History of Nearly Anything. Very entertaining and interesting. You ought to read it if you get a chance. While he was writing that, he came and visited us at the Iowa Survey, and he took a look at our facility, and he talked about the Manson crater. He talks about the Manson crater a lot in the book. Talks about our facility too there at Trowbridge Hall. Calls it a 19th century pile of red brick, which is pretty much what it is. Anyway, he also described the blast at Chicxulub, and he described it by a book by Lawrence Powell called Night Comes to the Cretaceous. And there, Powell estimated how much energy the Chicxulub crater would have been created. The blast there would have been 100 billion megatons as opposed to Manson's 5.5 billion. So it would have been a lot bigger. And how big was that Chicxulub blast? Well, he estimated that if he exploded one Hiroshima-sized atomic bomb for every person on Earth, that's 15 kiloton bomb for all 6.4 billion people on Earth, you'd still come up short about 1 billion bombs for the amount of energy to max Chicxulub. So that's pretty incredible. I came across another comparison the other day, and so I've included it too. It'd be equivalent of the Chicxulub blast out of Mexico would have been equivalent to blowing 1 megaton sized nuclear bomb up every 4 miles on Earth. So if we look at Johnson County, for instance, there's North Liberty up near the corner up there, or up toward the top of the middle there. This would be equivalent to setting off a 1 megaton nuclear bomb every 4 square miles. This is how many we'd have just in Johnson County. And you extrapolate that over the whole Earth, you can imagine how much energy was released by one of these impacts. Pretty incredible. Well, will something like this occur again? Well, Gene Shoemaker and his wife and others actually looked at what they call near-Earth asteroids. Those are asteroids that they see orbiting the sun today that cross the path of the Earth and could eventually collide with the Earth sometime. So with that, they came up with an estimate of a Manson-sized impact hitting the Earth about once every 1.2 million years. That's not very often, or that's pretty frequently. I mean, if you look at things geologically, you're talking about billions of years, 1.2 million. There would be a lot of them. That's pretty frequent. Fortunately, the Chicxulub ones are ones that, you know, wipe out all civilization on Earth. Only occur once every 100 million years, so they're not near as likely. One other thing I wanted to talk about Manson here was, if you look at U-Haul trucks, if you happen to catch the graphic that has Iowa now, they actually have the Manson impact structure representing Iowa. And this is what their graphic looks like. I worked with them a little bit when they put this together. You see the blast there where Manson is, and you see some illustrations of meteorites coming, zooming in. And then he has a copy of sort of my cross-section of the crater that I had. So you can see the central peak and the edge of the crater. He also put some corn stalks on there that at that scale, those corn stalks would be about 8 miles high. So, you know, they'd be up there colliding with airliners that are flying. So a little bit of exaggeration, but we are the tall corn state after all. So what the heck? And then he wanted a formula on there to make it all look real scientific. So I gave him this formula, which is a formula for how far particles get ballistically ejected out of the crater. So the grains of sand, etc., blasted out of the crater by these impacts. That's how far they go. So when you see that coming down the road now, you'll know that's what it's all about. Well, the other impact structure is we don't know near as much about it. It's up here in Decorah, Iowa, quite a bit smaller. Decorah now is about, what, 112 miles north of us. Well, Decorah is known for beautiful little scenic town with nice old architecture, Luther College, and these beautiful cliffs of Upper Iowa River. They're one of the better canoeing spots in Iowa. But we look at this little illustration, which is kind of an angular shaded relief of the Decorah area. There's the town of Decorah. Here's the crater, 3 miles in diameter. We have a drill well that goes right from almost the center of the crater straight down. If we compare it to the kind of rocks that we see outside of the crater, we see there's quite a bit of difference, particularly below that unit called the St. Peter Sandstone. Below there, everything is pretty weird in the Manson crater area. So the geology is certainly different than the area outside of the crater there at Cresco. We've originally thought that these were maybe some incised paleo valleys. At St. Peter Sandstone, when it covered Iowa, just before that was a period of real low sea stand. The seas were real low, and so the rivers and stuff incised themselves very deeply into the landscape. And so we see some of these valleys, deeply incised valleys filled with St. Peter Formation. We see those around. We thought maybe that's what it was at the time. But it turns out when we look at the Decorah structure itself on a little bigger map, we don't see any indication that those valleys either went into or went out of that Manson structure. So that's pretty much related to that structure. Well, we got mapping geology up there a few years ago, and one of our old buddies, Gene Young, she was a geology student at the University of Iowa who decided not to pursue geology, but she dropped out to become a hippie and live up in Decorah on a farm with other hippies where she grew plants and delivered the mail and did things like that. Well, she's also an amateur geologist, so she's exploring the geology of this area and came across some of these some of these newspaper clippings that say there was coal deposited, discovered at Freeport. Now, Freeport is right east of Decorah, right next to it there. Exploration being made now. Well, we certainly didn't expect any coal in that area, and the state geologist, Sam Calvin, said, no, there's no coal in that area. It must have been brought down by the glaciers or something like that. Well, what the heck? Later, 1922, they're still looking at this stuff and getting the coal analyzed and said it's good quality coal. So there must be something there. So we set out to look for it. We had never found anything comparable in that area until we got really looking there with Gene. And sure enough, here was an area just north of Freeport, right along the upper Iowa River. And there was something weird there. So our geologists went out to try to collect this. It was a little exposure right along the bluff of the river there. Above that is St. Peter Sandstone, so you don't see it outside the river. So our intrepid geologists had to go in to look for it. And there they are. Here's a little close-up to them. Now, Bob McKay was my office mate for many years at the Iowa Survey. Tom Marshall was a geologist at the survey at that time, works for South Dakota Survey now. And Derek Briggs, a very famous geologist, teaches at Yale, and he had to come and look at these things too. And right along the side of the river there and underwater, we found these big chunks of shale. Well, what the heck is this? So we decided we'd perch ourselves right along that exposure, right on the cliff there, and try to drill a hole down and see what we could find. So there's a St. Peter Sandstone in the background. You just don't see that exposed up here on the land, but you do see it in the river. And when we drilled a hole through, sure enough, it started out in that St. Peter Sandstone, but then all of a sudden we hit this shale, the Winneshiek Shale. Oops, let me go back to that. Usually a shale is just a mudstone, basically, and had a lot of other weird things in it. So we went back to all of the water wells that we had in the area, and we identified all of those that ran into this weird little shale. And you can draw a circle around all of them. And that's the same circle that we identified later as the crater. So when we mapped the geology around there, if you strip away all the superficial materials and just look at the rocks that are at the land surface after you get all of the river deposits and everything stripped away. Here's a town of Decorah. Upper Iowa River comes shooting through there like that. And here's the limits of the Decorah crater. Well, you see this little gray area on the lower right corner there. That's this Winneshiek Shale. That's this weird shale. So it's exposed underneath the river sediments, but it's only exposed at the surface on that one little spot there. We were lucky enough to find it there. So the drilling tells us, so we have a crater that looks something like this. You see that U-shaped feature there blasted into the other rocks. You can see where it cuts the upper Iowa River Valley there. Here's the well that we used to identify how deep the crater went. We saw, this is a little log of the well there. We see the first weird crater rocks occur right there. And then once we get down to about 900 feet, things seem to be pretty normal. Well, this is way too shallow for an impact crater. Craters are always much deeper than this. A crater this diameter, with 3 miles in diameter, rather than being just 0.2 of a mile deep, we would expect it to be 1.5 miles deep, because these craters form hemispheres, and so it should be about half its diameter deep. So what in the world's going on there? That's one of the things we still don't know for sure. Although when we look at samples that we collected from the drilling, we see that there's these chopped quartz grains. These quartz grains look like something that came from much deeper. And if we look at them in thin section, we find all of these fractures on them. Well, these fractures look like they've got some kind of a pattern, but they don't look like parallel deformation features. They're too far apart and too coarse. But there are multiple fracture sets in there. Well, fortunately, geologists from the Smithsonian, Bevan French is one of the top impact scientists in North America, really have been looking at these kind of features. And he said he looked at some of our thin sections and determined that those coarse fractures were, in fact, evidence of a hypervelocity impact. So those were evidence, in fact, of a meteor impact, just not as big a one at Manson. So they weren't quite as fine of impact features. But we got looking back at grains again, and we saw some of these parallel deformation features on the corners of some of these sand grains. So in fact, it did get enough energy to actually produce parallel deformation features. So for sure, this is an impact. And it turns out that Decorah was the 184th known impact structure on Earth. Well, getting back to the age of this thing, we know it occurred just before the St. Peter sandstone was deposited, blew all the rocks below that out. And so if we look at the geology of the area, here's an Ordovician geology. The Prairie du Chien group lies underneath the St. Peter, and it's 478 million years old. The St. Peter sandstone itself is 463 million years old. So that tells us the age of the Decorah impact was somewhere between 178 and 463 million years ago. That's a very interesting time if we look at the Earth, because there were a lot of other impacts about that time. This chart on the upper right shows a number of impacts at any given time on Earth, and you see right that period of time between about 450 and 480 million years ago, there were quite a few impact features found on Earth. And I showed them on this map here. This map kind of is a reconstruction of the globe the way it was back in the Ordovician. And the yellow dot is where the Decorah structure would have been. And these red dots are other impact structures that we know are the same age. Well, it's interesting. We look at these ones in Scandinavia here. There's a number of them. There's a quarry right near one of these impact structures called the Thornburg Quarry, and they quarry limestone there. If we look, they have these little pieces of meteorites that are trapped in the limestone there. These are meteorite fragments that were thrown out of those other structures nearby and actually landed in the limestone here. So we don't often get to actually look at the limestone. And so we've looked at those individual meteorites to learn a little more about them. And sure enough, these are meteorites. They're type L ordinary chondrite meteorites. Well, if you're a meteorite person, you know that type L ordinary chondrites fit in with here. If we look at the relationship between iron and sulfur and on this chart, and they plot right here, these are type L chondrites. Particular group of chondrites. 34% of all the meteorites that are known on Earth are L-type chondrites. Interestingly enough, these have a composition that is very similar to the composition that we determined from asteroid 433 Eros, which is one of the asteroids out in the asteroid belt that our instruments flew past, and we were able to get an analysis of it. So these same type of spectra as the L chondrites. So what we speculate happened here 470 million years ago, a couple of these asteroids out in the asteroid belt smashed together and broke apart. The debris came raining down to Earth, and it hit in all these various places. So here's a chart on the bottom that shows these various impacts that are about the same age, and Decorah is the star one there. And you can see the age on the bottom. So these are all about the same age. Now, we're not exact with our dating of things that are this old. So these were all probably in the same ballpark. Not that they all came in at once, but they all are pieces from that same blast that came in over a period of thousands of years, maybe even, but they all were from the same blast. Interestingly, also, if you look at that period of time, what you see right here at 450 million years ago is an extinction event, the Ordovician-Silurian extinction event, which is second largest of the 5 major impact events in terms of genera that were driven to extinction. So not only was the Decorah impact structure related to these other ones, it might have also been related to that extinction event. So that's pretty cool. You've got 2 impacts, and they might both be related to extinction events. Well, one other thing about this this crater, here's the map again, the Iowa River. That little circle shows where our exposure was. We get outside of the crater where we see the rocks that weren't blown out of the crater. Here's some Ordovician Oneota dolomite. This would have been blown out of the crater, but outside of the crater we see it. But what we see is this thing is turned over. So this is a little overturned flap like we saw at Manson, but of Ordovician Oneota formation. So that tells us the edge of the crater runs somewhere between that exposure and our exposure of the rocks inside of the crater. So we got a little bit idea of what's going on here. One other thing about the Decorah crater that's pretty interesting, the shale that we were talking about there, called the Winneshiek Shale. It's a shale that filled in the crater after the blast. It's preserved there, and what we see in there is an incredible group of fossils, to the point that the geologists call that a Lagerstätten. That Lagerstätten is a deposit of extraordinarily and abundant fossil preservation. This is something that you don't hardly ever see anywhere. So the fossils that are preserved inside of this crater are pretty interesting. And they include trilobites. They include a lot of things, but what we don't see are some of the common Ordovician fossils that we see in the limestones and stuff around there. So this was a very restricted environment. It wasn't a normal open marine environment where we see the corals and the trilobites and the graptopods and cephalopods and all of those kind of things. Very restricted environment. And the guys that were studying this at the time described that environment as being characterized by extraordinary fossils representing the fauna of an unusual near-shore marine environment. With that information, we send a grant to the National Science Foundation, and they send us money to do a little more work. So we teamed up with Smithsonian and the U.S. Geological Survey, the Yale Peabody Museum, University of Iowa. We all got together and went to work on this thing. With that funding, the first thing we did is build a little cofferdam around that exposure so that we could pump the water out and actually take a better look at the rocks that are there. So this is below river level now, but it's pumped out. And we can see, here's what that Winneshiek Shale looks like. Thin layers of shale. Now this shale is very fragile. It blows apart after it is exposed to the air very long. So we collected it. We collected about 2,000 pounds of it, and we had to keep it in these little storage containers that were filled with water, so we had to keep them submerged in water to keep them from blowing apart before we could study them. So we hauled all 2,000 pounds, all this stuff back to Iowa City and to our facilities there in Iowa City, and we slowly went through and split that coral apart and took, or that shale apart, and took a look at what kind of fossils we could see. Found a variety of fossils. Eurypterids, phyllocarys. Phyllocarys are like shrimp. Ostracods are little shelled animals. Mollusks like corals, lingulid brachiopods, and a bunch of unknown things. We found some plant fossils and some jawless fish fossils. So there's a variety of things found in there. But the eurypterids were one of the things that were most interesting. The eurypterids were preserved as carbon films. So this thing was didn't have any preservable hard parts. This is what a eurypterid looks like. It was actually a sea scorpion. It didn't have any preservable hard parts, but the material that was there, the organic material, was preserved as carbon. And there's so much of this carbon in this rock that it actually burns. You can hold a match to it and it will burn like coal. So this was probably the rock that they were seeing and thinking was coal. Well, these eurypterids are pretty weird critters. This at the time was the oldest known eurypterid on Earth, and these guys got pretty big too. As a matter of fact, the National Geographic came along and did a program on this site that they called The Strange Truth, The Day the Earth Fell. And you can find that if you want to look on National Geographic channel online. You can find that thing still on there and watch that show if you want. But they made a scale model of the Eurypterids that we were finding there. And this is how big they were. Pretty darn big. As a matter of fact, these Eurypterids were about 6 foot tall, as tall as a 6 foot man. So these were the prime predators on Earth at the time, and there were so many of them preserved in this rock that the rock will burn from their carapaces. Well, this model that they built was kind of paper mache type stuff, and it wasn't very strong. But we asked them if they build us one that we could use for display, and they did. This is a model that they built us. We take this out on display whenever we get an opportunity. This was at the Rock Show in Cedar Rapids in 2018. We would have had it at the Rock Show this year too if we would have had a Rock Show. But if we have one next year, you can bet that we'll have this there. You can come out and take a look at what this critter looked like. Pretty interesting. So those are the two impact structures that we know about in Iowa. As we say, there's probably more. If we use something like the moon as an example, there ought to be impact structures all over, but most of them are buried pretty deeply. This is our well database that we have at the Iowa Survey, and these are the only two craters we were able to identify in all that wellhead data that we looked at some 75,000 data points. There's a couple other points that are pretty weird. There's something going on, but we don't think it's big enough to be an impact structure. So that's about it. I've about run out of voice here, and that's the two impact structures for Iowa, and Manson and the Keweenawan. And I want to thank you for your attention, and I'll be online here a while if you want to ask any questions. Anybody still around?
There are 8 of us still left.
You guys get the awards for hanging in there for the longest time, I'll tell you.
Well, the few that dropped off left me notes and saying that was really interesting. So I'll be posting this recording.
Well, it's kind of detailed, but I really hate to pass by an opportunity to explain what these things are and how we discovered them, because it's a really interesting story, I think. If I was to live my life over again, I would study this crater for my PhD, because that's how interesting it is to me.
Does anybody have any questions?
I just have a comment. It's really a shame that you don't love your job.
Yeah, boy, I'll tell you. I used to, when I go on vacation or something like that, I would just be anxious to get back and get working on projects again. And when I went home from work in the evenings, I'd work on projects a lot. So when I retired, I didn't know what to expect, but I haven't really missed it. Retirement's a lot of fun too, especially with all you nice people around.
So you referenced a lot of famous geologists today. Do you, when you guys make a discovery that's really significant, do you ever get anything named after yourself, or is it always named by the city that's nearby?
Yeah, that's the normal procedure, is to name it after a geographic something you can find on a map, like Chesapeake Bay Crater or the Manson Crater, the Reese Crater. But, we don't need the fame, so what the heck. It was interesting, when we first started studying this thing back in the 90s, there was a program going on that studied meteor craters that was housed in Houston called the Lunar and Planetary Science Institute. And they'd have a Lunar and Planetary Science Conference once a year, and they'd bring everybody that got money from NASA to come and talk about all of their space probes and things like that. It was a full week of 3 concurrent sessions going on at the same time of the scientists showing off what they found with their spacecraft and stuff, and trying to impress NASA so they give them more money. So this was one of the best meetings. I went to this 5 years in a row, and I brought all of our information there and tried to get other scientists interested in it. And we did. We ended up publishing a publication that included, was co-authored by a guy named Christian Kolberl, who's now the head of the State Museum of Austria, and a very famous impact worker, and a lot of other impact workers kicked in on that thing. So we've got a publication on it that unless you're an impact scientist, don't even think about trying to read it. It's too technical. But we got that information out, and I'm always in hopes that we can get people to come back and study it again. I've got another student right now that's starting to work on some of this stuff. So lots of information to be gained yet. So a lot of projects.
You mentioned a fossil area in Winneshoot County. Is that visible to the public, or is that something that's kind of buried? Or
yeah, that's pretty much totally buried. If you know right where to go, you can find this shale unit, but you can't really see any fossils in it or anything. You really need to pump the water out like we did and collect some samples and bring them back. People had collected enough samples to be able to think it was coal, that it would burn, but really you can't collect any fossils there.
okay,
We still have hundreds of pounds of that stuff that hasn't been looked at yet, so it's very interesting.
Anything else? All right. Well, thank you so much, Dr. Anderson. You walked us through some very technical stuff. I felt like I was back in class.
Yeah, I'm sorry about that, but I like to challenge you, you know.
If you want to issue us a quiz, we do have a video, so we can go back and we have our cheat sheet video that we can watch.
Well, if there's anything else you're interested in, any aspect of geology of Iowa or anything like that, that was my job for a lot of years. I have lots of talks in the can that I can modify to give to you. This is probably about as technical as they get. So if you survive this, then you can probably survive other ones. If there's anything you're interested in, let me know. Be glad to do it.
do you have anything on the one out the reservoir, the fossil area out the reservoir?
You bet. Devonian Fossil Gorge.
Yeah.
Yeah, I've got one on that.
Cool.
Okay.
Well, then let's talk
that'd
about
be fun.
scheduling that.
Well,
Yeah.
schedule it whenever you want, and let me know.
Awesome. Well, thank you so much for joining us, everybody. And like I said, I'll send out an email with the link to where this is posted.
Thanks.
Thanks,
Thank you.
everybody.
This
Look
was
forward
fun.
to seeing y'all in person again.